Okay, so I think everything's live now. Uh, so, as you can see in the corner there, what I'm going to be going through today, just real quick, is some of the stuff from OCTF last weekend. Or, I'm sorry, OCTF is next weekend. The upcoming, this Friday is when it starts. It's going to be a CTF. It runs for about 24 hours. Uh, I'm sorry, it runs for 48 hours. I'm sorry, I'm a little bit out of it right now. So OCTF is going to run for about 48 hours. It starts at 8 p.m. Eastern if you're in the US, or UTC 0, convert that to whatever time zone you happen to be in. And so, what I'm going to be doing today is I'm just going to run through real quickly some of the challenges from last year's OCTF so that people have an idea of what to expect this year. Now, this isn't a great preparation method because the people who are writing challenges this year, not only are they not necessarily the same people, I don't actually have a ton of insight into who makes up the team. So OCTF is run by the Oops group. I don't actually know who they are. I might have met a couple of the members at one of the events over the years, but other than that, I just know they are Oops. They sometimes play as part of Bloop. And that's about all that I know. So, in any case, they're running an event this weekend. I have high expectations for it. Last year we played in it. I remember it being a ton of fun, and hopefully this year does even better. If we go to last year's version of it, we can see that it turns out, at least according to... Oh, where'd it go? I guess I can't see this without being logged in. At least according to... Oh, that's why I can't see it. Finals. For quals last year, at least most of the people who played in it thought it was really good. They agree with me that it's a lot of fun. Basically, if you come through here, basically everybody says it was great, max points, they thought it was amazing. So, why exactly is that? So, one of the... I thought I had this in the tabs here, but I guess not. So one of the things they did, which was a little bit different than usual, is they didn't do the X 100 points. That was a little bit popular last year. Instead of the easiest challenge being 100 points, it was 1 point. And I believe that last year only one team cleared the board, and I believe that's LCBC. Been like a year since this happened though, so who knows if I'm actually accurate about that. As you can see, there's a relatively large variation in points just in the top 10% or top 10 teams. Like, they did a good job of making sure they were difficult challenges that a lot of people had to put a lot of effort into doing. Other than that, they stuck to at least a somewhat standard set of categories for a Jeopardy game. You had your reversing and exploitation, you had crypto, you had web, you had a miscellaneous category. One thing that they did that was a little bit different, and I'm just going to kill all these tabs so we can go through them a little bit easier, was this mobile category. So the mobile category was, I'm guessing because looking at CTF time, they're associated with Tencent. My guess is that that was some of that interaction there. They did 3 challenges that were explicitly for mobile devices. In particular, I believe they were all Android devices. I wasn't the one actually looking at those challenges last year, so I don't remember that well. But just take a look at these real quick. And a quick note, thanks to the P4 team here, they have a ton of actual write-ups for this on GitHub, and they're really easy to read through. They did a very good job of writing these all up. So anyway, just to go through this real quick as an example, one of the mobile challenges was this Boom Shakalaka. Basically what they did was they gave you this Android APK, and if we read this right up real quick, basically what P4 did here was they decompiled it. They said, oh, look, it gives us part of a flag. So they looked through it and they saw that something is going to happen if you look at this XML file. they then decided to play this game because the APK was actually a game you played. I'm trying to remember what exactly you had to do in the game. I think it was kind of like a asteroids type thing, but I just remember somebody over in the other corner messing with it. But reading through this write-up, it turns out that no, just getting a high score was not sufficient. You had to get a specific high score, and once you did, and you set everything up properly, it was going to dump out this flag for you. Basically, it was, can you reverse and exploit a Android APK? And if you, well, not exploit, it's basically crack me, kind of, because you had to do like they built up this flag, and you just had to get everything right to get the flag out of it. Generic Android reversing. This was a 3-point challenge, so pretty similar to like a 300-point challenge in some of the other CTFs. So, other than that, there was also, let me get rid of this too while I'm at it. There was also this state-of-the-art challenge. Same thing, except Android had just introduced art. That is the Android art. There was art and Dalvik, basically 2 different runtimes for Android to run in. Most of the stuff, let's see here, Dalvik was introduced with, I believe, the first Android, where art started in Android 4.4, and it became the default in 5.0. So let's see if I'm right here. So this was in late 2014, so I guess art had been around for a little while. And basically, it was somewhat similar of a challenge. You got a APK, you basically pull things out of it. And if you take a look at it, like this is a write-up by, I'm not sure who, apparently it's somebody who at least sometimes plays with Shellfish. So anyway, but this was another Android reversing challenge. You had to do some actual ARM reversing, as opposed to the other challenge, which I believe you were able to mostly decompile it pretty straightforward. So if you want to take a look at these write-ups, they're linked in the CTF CTF write-ups. These 2 challenges have fairly full write-ups. The WebDroid one does not. So out of the 3 mobile challenges, only 2 of them have real write-ups for you. Then there were the fairly standard categories outside of that. There is a miscellaneous category, check-in. It's exactly like you see in a lot of CTFs now. The free flag to, basically the reason a lot of organizers do this is to differentiate between teams that register and don't play and teams that actually attempt to do something. Because if you take a look at the scoreboard from this, they had 875 teams register for OCTF last year, and if we come all the way down here, that is just the teams that scored at least 1 point. The number of teams that registered, I don't know how many do for this, but for a lot of events, it's twice as many teams register as actually solve even this very basic challenge. So by having this basically giveaway challenge, it gives the organizers a good idea of how many people actually even attempted anything. So they had just the super standard, did you even take a look at anything? They also had this challenge that they called OPM. Again, P4. They've got a good write-up on here of what it was. Basically what it was you had an image, and they used StegSolve to pull out a thing from it. And it turns out what they pulled out the first time was a PK, was a zip file, which they recognized through the PK signature. You unzip that, they have a file which had this title, which is an ARM assembly instruction. So they opened that up, and it turns out, oh look, this is ARM assembly. So they went through this dump, they converted it from just this dump into an actual disassembly for it. and they went through it. And it looks like they used the retargetable decompiler. This is a online decompiler where you're able to give it some assembly, and it's going to try and give you a some source code. I don't have a lot of experience using this, but I have seen a couple times people try and use it, especially if you don't have like IDA hex arrays. This is the, as far as I'm aware, your best bet for trying to get automatic decompilation of a binary. And in any case, they did this, they wrote some Python, and they got out a flag for it. So, not exactly a straightforward challenge, but something that's definitely, here are things that you can step through and get a flag out of. And definitely something that belongs in a miscellaneous category. And then the other challenge out of here was XOR Painter, and again, P4. They have write-ups. It's great. Basically, what they had here was they had a CSV which had just a list of rectangles, and apparently, what you had to do was you had to take each of these rectangles and you overlay them on a bitmap, XORing what the bits are every time. So, they've got an example here of what it would look like. So there was a rectangle from 0, 0 to 3, 3 that was drawn, and then a second one which was from 2, 0, 1, 2, 3. So they draw a rectangle and then another rectangle on top of it. And basically, according to them, this is a thing. And then they wrote a script which generated this 16,000 by 16,000 pixel image, which apparently eventually popped out a flag. So, okay. Again, definitely a miscellaneous type of challenge. So, that's the miscellaneous category from it. Both of those were relatively small. If you remember, there were about 80 points for LCBT, and if you look at some of these other categories, I believe those were the two smallest categories for OCTF, the miscellaneous and the mobile challenges. So, in the crypto challenges, those were some interesting challenges. There were 4 of them, as we saw looking at the write-ups here. Basically, it was worth about 18 points to clear the category. I don't know how many people did actually clear the category. One thing that I thought was a pretty interesting challenge from like a design perspective was equation. So equation was, here is the RSA private key, and here is a picture of the RSA private key where a chunk of it had been blocked off so you couldn't read it. So what do you do? Basically, what this challenge amounts to is going through and actually understanding what exactly goes into RSA private key. And basically the answer is, well, it's ASN1, and we're going to have to go through this, we're going to decode it, and what do we actually know is in here? And if we keep going through, we're able to see that this is actually a really good write-up to go through it real quick of how to generate it. Basically what happens is that you're able to see in that binary all of the pieces to generate the other pieces because they gave you the second half instead of the first half. So just, again, P4 has a write-up. It's real straightforward. Actually, I think that might be the write-up I was just looking at, or very similar to it. Basically, they generate it, they then create a new key from it, and they get a flag. Pretty straightforward. Well, straightforward if you understand all of the encoding going on behind it. The other crypto challenges were at least somewhat more standard crypto challenges. There was the RSA challenge, which was this like a standard RSA primitives type crypto challenge. I'm not exactly a crypto expert, as you may have seen if you saw some of the earlier challenges, but this was basically trying to figure out, you're basically trying to create a key out of these parts. Then there were two other crypto challenges. Only one, oops, this is not what I wanted to be. Accidentally clicked on the P4 write-ups for it as opposed to the general write-ups. The other one that has a write-up here is People Square. Then I guess if I would have known that, I could have gone to it from the P4 one. This was another crypto challenge, except that it was a binary which was doing it. So you had to actually decode it. It looks like this is the hex rays decompilation of it. Actually, maybe it is. I'm not sure now. Anyway, you had to decompile this binary or reverse it manually. Going through it, it looks like they set up a 4-round AES. You had to do a lot of actual crypto work. Like going through this, there's a lot of real crypto work for trying to break it. It looks hard. It looks like the kind of crypto challenge I personally would not solve and would try and hand off to somebody else. But you can solve it. More power to you. Crypto is not my thing. But yeah, it looks like a pretty solid crypto challenge. So, the categories that are a little bit more of my thing. The exploitation challenges, I don't remember them all that well, and unfortunately, 3 of them there aren't write-ups for, and those 3 I remember almost nothing of. I remember looking at Jeep, in that there was something that was memcached with Jeep, and that's all I remember. I believe I was looking at that at like the very end of the competition. What I do remember was zero storage. And zero storage, there's a write-up here. Sorry, I don't know exactly who this is, but there's a write-up here. Basically, there was a use after free, and the trick for it was you were able to hijack the global max fast. And what that is, if you haven't ever looked at it before, How to Heap from Shellfish is a great resource for learning how to do heap exploitation of binaries on DL Malloc. What they've got is a simple file, which is an example of a specific heap exploitation technique, which describes what it is, how it works, and all of that. And for a lot of them, they also have a CTF challenge. In this case, the bug from zero storage, or the exploitation method, was this unsorted bin attack. Basically, at least for this solution that they used, there's a trick in how the unsorted bin works that lets you write the pointer to a freed block basically anywhere you want. It's a little complicated in how you get it set up. Definitely read through this for if you've never done it before. The basic trick involves there's a known pointer to a location for you to be able to get that free to actually work. In this case, they're able to use that to eventually... How exactly did this one get worked out? Basically, you get to Malloc there and get something out of that. There were several other exploit challenges. This was one of the bigger categories. Warm-up was just a very standard, here is a relatively low point value pwnable. Sandbox, if I remember correctly, was a sandbox breakout where you had a sandbox process. Unfortunately, the write-up here doesn't appear to work anymore. At least I can't get to it right now. The other category that had a lot of challenges, but unfortunately there are almost no write-ups for, was the reversing category. I do remember Momo very briefly. I believe there was... unfortunately, I haven't actually looked at this since then. If I remember correctly, though, The way we solved it involved writing some IDA to go through and fix up the binary in order to get a flag out. So, yeah. And then there was Trace. This is the only one that has a write up on GitHub right now. But basically, there was an execution trace, and you had to actually do something with it. So for P4, they basically took that, they dumped it back into a binary, and it looks like they turned that into something useful. And we'll go down through all this. Ooh, they even have pretty graphs. Look at that. Showing what exactly happening. Basically, it's a reversing challenge with a little bit of a twist. Instead of having a binary that you had to reverse, you were given a execution trace that you had to figure out what was going on in it. And in this case, they wrote some scripts to actually dump things out, and eventually, they got a flag out of it. So, those are the reversing challenges. Like I said, unfortunately, there aren't write-ups for most of these, and it's been almost a year now, so I don't remember at all if we had any progress on the other three. So, after those categories, there was the web category. And the web category was kind of interesting. There was one challenge that was kind of a two-parter. That was the guest book challenge. So for part one, let's pull this over here. For part one, there was some cross-site scripting stuff. I didn't actually look at this, so I don't know really. But this is a write-up that claims to work. Then there was a second part that apparently only 2 teams solved. My Spanish, not so good, so I don't actually know what this says. But apparently there was some DOM clobbering and browser anti-XXS that they had to use. That got them 1 flag. And then there was some Redis injection, maybe? I haven't actually tried to read through this with some, like, putting this through Google Translate, but it looks like it's definitely at least somewhat readable given all of the source code here. Other than that, one thing that was kind of interesting about this CTF was that it looks like they were relatively cross-site scripting heavy, in that that's not something that comes up a ton with web challenges. It's kind of hard to run them just because you have to have a browser constantly checking things. But as far as I can tell, and I remember, a number of their challenges were actually solved that way. Both the guest book and Monkey were apparently that kind of a challenge. There was also, why do I keep doing that? There was also Pia, which was some, basically there was this filtering validation, and you were able to basically get some you were able to inject deserialization due to how the filter was triggered. I didn't actually do this on the real challenge, but looking through this, it looks like what you're able to do was basically when the filter goes through and removes things, it will change the length if so. Look at this. It's going to replace select, insert, update, delete, or where with the string hacker. And the trick here is that hacker is a different length than where, and they were doing this on serialized strings. So basically, you took where, you replaced it with hacker, so now the string was 1 byte longer. So you were able to then do this deserialization attack against the application. So, yeah. And then finally, there was Rand 2, which seems to be fairly straightforward. Basically, they called Rand, they gave you the first output. There was then an MD5 of some other outputs, and you basically have to give them what the 5 outputs that were hashed were. So P4 solved that by they just brute forced it. They checked to see if they got the first seed, or they called Rand. They tried to see if they got it. If they did, they checked to see if the hash matches, and they put together a Python script here to dump it out and see if it works. Relatively straightforward, it looks, and apparently it worked for them. So, yep. So that's just a real quick wrap up of what zero-CTF last year looked like. I don't know how useful this is for people. I think it's pretty useful to go through and take a look at what the previous year challenges looked like. Not necessarily to know what this year's challenges are going to look like, but more to try and understand where the authors are coming from. It's a good idea to at least somewhat get in the right frame of mind. So, an example of this is part of solving challenges is trying to guess, well, where would the author have put the bug? Looking at how this challenge is built, where would a bug live? So looking at the exploitation category, they don't shy away from, some of the harder heap exploitation stuff, because in that case, this was one of the first challenges. So last year, there were a series of challenges which took advantage of this same bug. I believe, or the being able to write that arbitrary pointer due to I don't remember what they're called now. Sorry. I'm awful about this. The unsorted bin attack. If I remember correctly, so there's several of them that are kind of related to this, and I believe this was the first one that year that did that. In addition to that, there were a ton of exploitation challenges. They also had several of these mobile challenges, so it's probably a safe assumption that this year they're going to have the same thing, where here is an APK, you're going to have to reverse it. It's probably a good idea to get the standard like jar to deck stuff set up on your machine ahead of time. It's probably just going to save you a few minutes during the competition. The web stuff, it looks like they were kind of heavy on cross-site scripting last year. I don't know if that's going to be the case this year, but it's a good idea to keep it in mind that that might be the answer. Then there's the crypto stuff. I don't really know enough to say one way or another what to expect. Everyone I talked to that is a crypto person said that these were pretty solid crypto challenges, though, so it sounds like you should expect basically good things from all of the categories here. So, again, I have high expectations. Hopefully it'll go well. So, we'll see. So, that's all that. I'm going to take a quick break, and I'll be back in a few minutes. So, thanks, everybody. I'll be back in probably about 5 minutes here, so let's see if I can get this to work real quick. Okay, so that wasn't actually 5 minutes, but I think that's plenty of time. So to just go through things real quick, sorry, unfortunately, I think that might actually be playing, so I was going back and checking the video. So anyway, now, since I've gone through the OCTF stuff for next year, let's take a quick look at rocket science. I know one of the people who watched the stream last week when I went through Time Machine said they were interested in seeing rocket science. So I haven't actually looked at this challenge before. I glanced at, there's a couple write-ups that got posted in the IRC after the competition. One of them was from, I going to probably butcher this name, aren't I? Oujin posted a solution. My guess is that that's somebody from LCBC, because apparently they were one of... So they were the first team to solve it. I don't know if they were the only team or not. I don't have access to the scoreboard to see that. There's also a version in the IRC from Ocean, who's one of the organizers, who wrote this challenge. And looking at these write-ups, and I'm being a little bit loose in the term write-up, they were... What both of these scripts are is they're basically just raw Python scripts with little or no comments to go with them. But looking at these, it looks like rocket science was definitely a virtual machine that I come in here, I run this, like I take a look at this file rocket science that says it's a 64-bit x86 self. However, looking at these write-ups, I'm not convinced that's actually true. But take a look at this. So there's rocket science. There's a robo strike. I've got 4 options here. I can exit. I can strike all unicorns. Okay. I can define an objective. Okay, that does a thing. And yeah. I don't know what these do, but looks like they do things. So that's what that is. I'm taking a look at the actual binary. So what does the binary look like? So this is, I've opened up the rocket science binary in Binary Ninja. And taking a look at this, this definitely seems to confirm that this is probably a virtual machine, given that they're going to initialize a CPU up towards the start of main. They're going to call this print banner. And what is this print banner actually doing? So they are calling puts. They're going to put us the robo strike. They're going to print out... What is this? They're calling base64 decode before they put us it. So they've apparently base64 encoded whatever this string is. They're going to put that and they're going to welcome. So looking at this, my guess is that this is this thing base64 encoded. Okay. They're going to print that out. Looks super simple, and there's nothing I can actually touch in here. I don't actually know about this base64 function. We might come back to it later. And there's a menu. Okay, there's a menu. So I get to define an objective. This looks basically exactly like I would expect it to. There's a read function. One thing to note here is that they might not be decoding. Yeah, it looks like Binary Ninja is not decoding this right. It thinks that this should be a struct instead of a constant. It's possible that I'm using a slightly older version that has locked up for me now. Come on. Well then, it would appear that my oh, there we go. I'm not sure what just happened there. It looks like it spiked the CPU and did not like that at all. Anyway, what I was saying was that it looks like they've decided that what should be a constant here is actually a struct because they recently added the struct features to Binary Ninja. It's a little bit overzealous sometimes about trying to identify what exactly the structs actually are for the ones that it knows about, or the types it knows about. But looking at this, look like there were symbols in here already. There is a CTF read SN. Just looking at the arguments, it takes a int32, star, and a uint32. Based off of these, this is probably the buff you're going to read into. One of these is the number of bytes you're reading. The other one is the character you are comparing with. So we take var c. So var 20 is what we read in. We're comparing against that. This is probably the length, would be my guess. The var c, though, is... So we're calling read. The arguments, let's switch over to this. So we're calling read, where we're reading from chapter 1, we're reading into that buff. Yeah, I will totally buy that this is basically a read line functionality, right? We're reading up to 7 bytes, looking for a null line. We're then going to call A2I on it and return that back. Right, we returned that. Called A2I. REX will be the return. We haven't messed with REX here. So we then save this off here. So if menu op is greater than 6, we're going to come over this side. Otherwise, we're going to come over this side. Basically, what we're going to do here is we're going to calculate what is. This is some sort of a jump table, and we're going to jump to it. Okay. Do we actually know? So we took the bytes out of that. So we took, okay, I'm gonna have to think this real quick. So we took the option we sent in, we then shifted over by 2, multiplied it by 4, multiplied it by 4, that's right? Yeah. Put it into RDX, we then pull out this, we read out pointer, or we're going to read out a D word at RDX plus RAX. We then take that, we convert it to a quad word, and we set it into RDX. This is, yeah. Then we're going to do an LEA of that value again. We're going to add RDX to that, and we're going to jump to it. So it's just a pretty standard jump table. So basically, we have values here. Let's actually do that real quick. So we have these. This is a... I want to view this in the hex editor. So we have some bytes here. Those are our bytes. Does that work? Oh. It looks like it's not gonna let me. Anyway, not gonna let me do that. Okay. So I want to do, I'm sure there's actually an easier way to do this, isn't there? I want to, actually, if I change the type of this to an int, yeah, look at that. Actually, I want to make this a, I want to, no, go away. How do I undefine this? Fortunately, I don't believe I have one of the developers actually over my shoulder this time. So instead of that, I want it to be four of those. I believe it's five of those. No, it's more than five of those, isn't that? It's like it's seven of those. So these are the pointers here that we have. And basically, if we go back to what the binary was doing here, we took out the value. We add the D word from that. So we take out a D word from there. So those values that I just turned into an array. We add that to this. So coming in here, if I sent it 0, it's going to run CF1C, CF1C plus or minus OX3464. So if I go, 9AB8, go here. This is a function. Take a look at, and basically it's already identified that this is a function. I want to create a function here, and this is opt0. I believe that's because they've done some of that analysis for me. Don't quote me on that, but my understanding is that at least a lot of the time what they're doing is smart enough to understand that. So anyway, we then have opt1, 571, which is 99AB. This is also a function. Create a function here. What do we do here? We set this up, and then so what are we doing? We're going to read an argument to this, it looks like. We put it into RDI, and we do a CPU set objective, and then we jump out to up here, we jump here, we call menu, and we basically loop back around. Okay. We have an option 2, 55D, which is 99BF. We're going to make a function there. Looking at this, it's probably a safe assumption that these are all going to be functions, aren't they? So what I'm doing here is I'm looking at this and I'm saying, you know what, 48 something looks a whole lot like a function prologue, in that's basically what all of these have been doing. So let's just decode a couple more. And looking at these, it definitely looks a lot like these are decoding properly. I don't know if they are or not, but those look pretty well decoded. So if we come in here, we see that we had a CPU set objective. That was option 1, if you remember. Come in here. What exactly is this doing? And I'm going to go back to the graph because I find this a little bit easier to read. I know some people prefer the linear view like that. I am not quite old enough to be one of those people who has to have their linear view. I know there's a definite population of people who learned how to do reverse engineering before the graph views became popular, so all they use are linear views. I started doing this after the graph views became popular, so graph views are what I'm used to. And when it comes to reverse engineering, a lot of it comes down to what tools are you used to looking at, because you've gotten so used to looking at stuff in your tools that you're just that much more efficient at it. So anyway, we have the CPU set objective, and we set an objective here. We're going to call this readsn, which we said was basic. I want to change this, so I want to change this type to just int. Just an int. Okay. So for whatever reason, it does not want to actually let me do that. Looking at this, what are we doing? Things are getting a little bit closer. The elf header is based at 0. It is thinking that this is the header. I would like to point out that despite the problems I'm having here with this, I know that this is something that has been fixed recently. If not in the build I have, it's been fixed in a different build. It's something that they're well aware of, and it's something that I will work through a little bit here and be annoyed at. But in general, shouldn't be something annoying. Oh, what are you doing there? You're not going to let me do that, are you? Okay. Well, that's fine. So we specify an objective ID. That's going to get saved into this. We're going to set a token. We get to specify an objective. Then what do we do here? Okay, I'm sorry, this is not working. So what I'm going to do here is I'm going to switch back to the released version. Basically, there are two different versions of Binary Ninja. There's the release version and the un version. So I'm switching back to, I'm sorry, there's the release version, the, what is it, development version? Yeah, the release and the development. I usually use the development version because the Binary Ninja developers are great and they're super responsive to bugs. For whatever reason, this is not liking that at all. So, like that, the way it was whoa, what did I just do? Oh. The way that it was handling those. Why is it still doing that? Huh. Okay. We're going to delete that and start over. What we're going to do here. Whoa. So, where are we going here? So one thing to note here is that, like most of these tools do, Binary Ninja gives you these BNDBs. They're roughly equivalent to the like IA64s or IDBs that you're used to with IDA. And so we can see here, now it's still doing the same thing, but because we don't have types here, like they've just been a little bit aggressive about trying to identify what these are. One thing, oh, I remember how to fix this. Well, I remember what's going on. Basically, what they've done is, because the binary is based at 0, it thinks that the because the 0 is there, that it must be referencing that. But I don't remember how to fix that. So, well, like I said, but at least this is a little bit easier to read, to the point I can live with it, at least for now. So going back to what we had here, we had this right here, and we said that this was a int 7. So there were 7 integers there, and I want to Well, if I'm not going to get it to work, I'm going to switch back to the development build. So I just asked in the Binary Ninja Slack, if you're not in the Binary Ninja Slack and you're using Binary Ninja, I highly recommend it. They tend to be super responsive. There's a ton of different people in there who are always asking questions and answering them. So I asked in there how to fix this. I'm sure that by the time I get everything switched back over, I'll probably have an answer. So we've now done all that. I'm going to close without saving because I haven't done anything useful so far. We're going to reload this. And let's do this again. So we've got this again. The same thing. I want to change this to change this type to an int. I then want to change it to an int 7 because there's 7 of them. And then I said I want to do hex ox cf1c minus ox 3464 is the smallest one, right? Yes. So go to 9ab8. Made a function there already. Function there. So again, I'm cheating again like I did before. Basically, I know that the way that these functions look, the start of them starts with that 4.8, so I can kind of just come in here and make it a function as I go. I don't have to actually go through and do the math because I know basically what that was doing anyway, so I'm just going to skip ahead a little bit. So, looking at these, that's an interesting function right there. What is that doing? So there's a call CPU debug, which is going to do something here. It's just messing with some of the arguments. So this is the... Am I not going to be able to name this directly? Okay, I guess I can't name this. But so this right here is the CPU object, is at this RBP minus FC8. So we set it to debug whatever this does. So this debug is going to, what exactly is this going to do? We take RDI, which was this pointer. We set it here. We put that into EAX. We move a value out of that. Then we pop RBP and return. And we push it up here. Basically, this is getting, it's probably getting the debug state is what this is doing, isn't it? Okay. There's also this insert command option. So let's go back to that table. So this was, where were we? I want to know hex ox 9a60. I'm going to go this way, minus ox cf1c. So 3, 4, bc. So option 6. What does option 6 do? Option 6, 5, option 6, 5, option 6, 5, option 6. Oh, we have to set it into debug mode first, don't we? That's what that's doing. I don't know that for sure. I'm kind of guessing here. So if debug is 0, we're going to jump down here and basically bail out. Okay. If it is, then we're going to come in here and we're going to execute a command. So we want to set it in debug mode, apparently. What does execute command do? That's doing a lot of stuff, isn't it? Okay. So what do we say this was? This was the CPU, or this is exec command. So since we're now to 8 o'clock, I'm going to cheat a little bit more and I'm going to read what the solution looks like. So the way that Ocean solved this, so he has a do exploit function here. Actually, here I will. So there's a do exploit function. He generates a OID, a token, a content. There's a store objective, so he stores an objective to leak out the vtable, and does that by create. So R is the. So basically, there's a stage 1 shellcode, which is going to actually. According to this, the stage 1 shellcode enables debug. It. So I know nobody can actually read this other than me. So reading through this real quick. There's a stage 1 shellcode here, which enables debug and move vtable pointer to allow leak and leak vtable pointer easily. Okay. So we move 1 into A, load 1 into A, I think. We then write A to that address. We then load that into A again. We subtract 8, and we move it there. I don't actually know what I'm reading here. What about this other one? So in this other one, there's another write-up that was posted in IRC. This is one of them. The other one was just on Pastebin. Look at this. They both set an objective as one of the first things they do. So let's go take a quick look at what set objective does. So set objective. Which of these was set objective? Set objective. So set objective. There we go. We read an objective ID, we read an objective token, we read in a objective, and then what do we do? Oh, we're doing a stircat in here. Well, that's not good, is it? So what exactly is 618? So 618 was the objective ID. It's kind of amusing if, again, if you guys aren't in the Binary Ninja Slack, basically Jordan, who is one of the developers, is trying to find where Josh, who is not one of the developers, wrote the solution to the problem I have right here. Josh is on mobile, so he can't actually respond right now. Well, he can't find the solution and paste it. So Jordan is going to find that because Josh is just on his phone. I find that hilarious. Anyway, so going back through this real quick. Again, ignore it. It looks kind of gross right now because I haven't fixed this up. And oh, Jordan's typing. I should have a solution soon, shouldn't I? Oh, he's actually going to have to look at the source code and figure it out. So we said this is objective ID. And FC9. What is FC9? FC9 is something else. What exactly is FC9? So what are we doing here? So we said that this, wow, what is FC9? We're going to cat objective ID and FC9. Then we're going to so stircat takes RSI and adds it to the end of RDI. So they took that, they put it at the end of this. So I don't actually know what this is yet. Interesting. We then do some other stuff here. We're basically just moving things around a little bit. We're gonna call stircat again, this time with 5D8, which was the objective token. Actually this memset is probably important, isn't it? Yeah, so we're going to memset whatever this length is to 0, probably. That's my guess here. So we stircatted we basically stircatted the objective token and the objective ID together in this memory address. Token ID. And so there's some struct here that once I get all this fixed up, I will know the size of, and we'll get that fixed up. We want to specify coordinates calculation. So they printf that to us. They're going to read in some bytes here. Ooh, this is pretty long. I assume this is a length. We read that in, and then we execute command. Interesting. So execute command isn't some magic thing that we can't do anything with. It actually does something useful. Okay. And then we're actually going to call store objective 2. So what does execute command here do? I just got to kind of trust that these things are correct. So they zero it. They do something with RAM here. They call, do some stuff. They're going to base64 decode it, and they're going to run to none. So yeah, this is, reading through this, I am pretty convinced that this is a VM of some sort. You know what? Let's actually give it a try. Let's see what happens. So, oh no. Oh. Okay. So we have the script here. One of our options here. So let's see how I actually run this thing. So if length is greater than 1, then it's going to be that. Otherwise, it's that. We try and exploit like that. So I actually need to run this. Yes, no, maybe. Yes, no, maybe. So eventually we need to tell it a flag ID for it to know what to cat out. That makes sense. And if we don't give it one, they're just going to run proc. Proc is okay. So I want to do exploit none 1 2 3 4 and /rocket science. That work? Checking for new rules of Pwn tools. No module named common. Why does that not work? I assume that's Pwn. So I assume that this is the Pwn tools common. Right? No, it is not. So this is some sort of common library that I assume is one of the shellfish things. That's unfortunate. So I can't actually just use this, can I? I assume this is like they had a common library that they had set up to do some of their exploitation stuff, so I can't just run this. That's unfortunate. So we're going to fail here at some point, but what I can do is I can just do whoop. And where do we use this? So, whoa, what happened? There was somebody did a thing. I see. So if you notice in the corner there, turns out the author is watching this right now and is correcting me because you know, I'm just wrong. That's okay. So what's actually happening here? They tried to run AS. It exited because it doesn't have the slightest clue what to do with this. Okay, I will buy that that's a thing. So, what are we doing here? So we tried to compile all this. When did we compile all of this? It's a Z80 assembler. I need to make my AS support Z80, don't I? Nah, it's okay. At this point, I'm not sure how far we're gonna get here, so I'm trying to bash my head against this and see what happens is probably the best bet. So what exactly does the Z80 look like? So I've heard of a Z80 before. I know that it was a thing before I was born. What exactly is a Z80? It's the most commonly used CPU of all time. Interesting. Oh man, 2.5 megahertz to 8 megahertz. Wow. So, oh, it's an enhancement of the 8080. Okay. Makes sense. So, what are we gonna do here? So, the common stuff isn't going to work because it has the assembler. I don't have the assembler for that. What are my other options here? I just want to watch this thing run, so. Don't try this at all. So it looks like it's doing a thing. So line 93, it sleeps. If we accept, we sleep. Okay. I want to get rid of these 2 lines, 3 lines. So one note here is what the author is doing here was they were basically designing this to actually work on the real game floor. So for iCTF, you didn't need to just run an exploit once. You needed to run it 300 times every 5 minutes because there were 300 teams out there that had flags you could get, and every 5 minutes that flag changed. So basically, you needed to keep throwing this all the time, and every single team had all sorts of different defenses that were in place, so there's all sorts of different reasons your exploit could fail. So what the author was doing here, I assume, was they were assuming, you know what, some percentage of the time my exploit is going to fail. Maybe this isn't a 100% reliable exploit, maybe they patched something, I don't know. So all I'm going to do is, every time it fails, I'm just going to sleep for 3 seconds and try again. So, what happened here? So we tried to set up a leak here. Ah, there we go. Where is this? So this is line 106 is where we failed. So store objective is not part of the binary. Okay. So what is store? Store is accepting R. R is that. I can write that real quick. So def store objective R void token content stage. What are we sending here? So we want to do ID token content command. So what I've done here is so this is the code from the other solution. This is the other solver had a set obj function in there, so I've just set up a store objective with the same stuff, and Oh, I should make the arguments fit too, shouldn't I? ID token content command. So I actually, so because if you remember, because I'm doing that, I want to actually return something here. So what just got shared? Ah, look at that. Oh man, your code looks so much better. So Ocean sent me the code that he used for store objective and read objective, and this looks, that looks like a lot more useful than what I was using. Not really, but. So we're going to have a store objective here. I want to just do that. So this is the code that just got sent along here. We have remote. Man, look at that! It's a doc string and everything. I'm not sure I believe this is a real exploit, given that like there's a comment there with a doc string. Like that just seems like crazy talk. So what we're doing here, we were waiting on something. Okay. Oh, apparently I cannot copy properly. Oh. So Slack was trying to be helpful, and because it was, a snippet, it was trying to add things. So specify objective ID. So it has printed out things, and now there's an invalid token because we tried to have a leak. So we can also look at that. Yep. So if I want to make stage 1 just a thing, I can use the. I can use this. Whoop. Now I want this thing right here. I want to open link. Build. No errors. That's just crazy talk. I don't even want to know where this thing got to. Okay. Did you really do that to me? Okay, where did this thing get to? Oh. So one thing that comes up that I would assume most people who play a lot of CTF are used to is you got your nice scoreboard which has binaries that you download. Where do they go on your system? And trying to keep track of where the current download directory is a complete pain. Before every event, I try and make a new folder and do that. Sometimes I actually do it, sometimes I don't. In this case, it looks like I actually did. So, look at that. We have a binary. So, I want stage 1 to be, I want numbers again. So I want to hello.bin.read. So stage 1. Oh, look at that. It did a thing. So it looks like when we turned on debug, it actually prints out all the registers and stuff for us. That is super convenient. So since we have all of this set up, let's actually walk through and see what this is doing. Because I think at this point, I've got about another half hour here. So I'm not going to be able to actually land all of this, but I can get a little ways here. So what we've done here, r.proc.prockety, I think that's right. Nope. maybe it's just PID. So what I'm doing here is basically I'm just printing out the process ID here. So I want to do, so what I've done here is I have the process ID printed out, and it is currently waiting for input from me. So I should be able to come in here, attach to it. And what I want to do is I want to break in at, where do I want to break in? Let's actually break in right here. So I want the linear disassembly here. I want to break in at 98CD, which of course isn't going to be easy to do, is it? Yeah. Blah. Oh, I can just do. Yeah, look at you, GDB. You actually have symbols for me, don't you? I want CPU run to NOP, don't I? So we've now run to a NOP, and we have the CPU state. So what exactly does the CPU state look like? So first off, did I write a response over here? I did not. So when we run to a NOP, what do we do? We're going to come in here. If this is the debug flag again, we have a debug flag. If debug is set, we're going to dump out the registers. Otherwise, we're going to read. So otherwise we come in, well, regardless of what we do, we're going to come in here. What are we going to do? So we call CPU read with an argument of, so rax is, so rax is almost certainly the CPU object, right? Yeah. So this is CPU. So we've called that at offset 8030. This is, CPU is huge, is what we're saying here. We supply that as, of course, the first argument. So this is the this pointer, because so this is for people who aren't that familiar with reversing C++. This is a C++ binary. They wrote C++ source code for this. So when you're calling a method on an object or on a class, the first argument is almost always going to be a this pointer. In this case, it is the being passed an RDI because it's 64-bit, and that's the first argument. Then in this case, the next argument is what we actually care about. So coming up here, right? Basically, the dump regs function here doesn't take any arguments. So if I wanted to, what I could do is, so I have that this pointer there. I could call CPU dump. Oh, there's two of those. Dump regs, and I want to call it with OX. Or let's do this the other way. CPU OX 561B42EB3C20. So I want to call CPU dump regs with the argument of CPU. Oh, of course, it's not going to work that well for me. I was so hopeful that that would actually work. That's unfortunate. I was hopeful that that would work, but So one of the problems is that since I don't have source code, GDB isn't quite sure what to do with this. So I can't just call functions out of that. But taking a look at this a little bit closer, what exactly is dump regs doing? So looks like we're building a string. We're pulling out all these values. Looks like we're generally having a good time. Man, that's a lot of code to basically print out a string with the current register state. So there's registers in there. Great, we know that. We call read, and what we're going to read is whatever is stored at this offset. What is stored at this offset? But we're also going to call this PC str. So we read here, edx is what we're reading in, edx is this. Is this getting, ooh, okay, so luckily we get to see that this is something that gets used a fair bit. And in particular, it's going to get used in dump regs. So if we come over here, we read this value into EAX, we upconvert it, and don't get to actually see why are you doing it this order. Okay, so what I was hoping for here was that it would actually oh, I can look at this way, can't I? Scroll. So we took this, we saved it into this. So this is the thing I want. So basically we put this in here. We then called this, and which order did we do this in? So we call, so this is actually what I care about. Right? So scroll. So I think I should see this in here. Yep. So this is, oh, okay. So it turns out that it's PC. Would make sense, wouldn't it? Go back. Oh, sorry. Everything appears to have locked up on me again. So we're going to sit here. So I might not have been all that clear about what was going on there. Basically, what I did was I know that the dump regs function prints out all the registers to me. So because I saw that there was some argument in the CPU structure, I look at that offset into the CPU structure, and I see that there's a cross-reference to it in another function. In particular, I saw that there was a cross-reference in dump regs. So what I'm able to do is I go into, oh, there we go. We want to go all the way back here. So in dump regs, I see here is where it's being used. And then I came down here, because basically they're building a string around it. And I can see that this is probably PC. And basically what we're able to do here, and I'm just going to do this real quick to demonstrate this. So if you see here, they build this PC string here. And looking at what the dump regs does, they put this, and so they put PC OX into RSI. They then load that with, oh no, I am totally wrong, aren't I? Okay, so they take that, they print it out there. They then have the var I care about and the thing I want, because I used useful names for this. And they're going to print those out afterwards. No, that's right. Yeah, so they print out PC OX this. Then there's the var I care, and they're going to print out the thing that I want. Again, being great with my argument names here. They're going to print out some other stuff, and then Z. So if we look at what this output looked like, looks like that, basically. So jumping back over to what this looked like. Basically, unfortunately, this is it's a little bit difficult to reverse some of this stuff sometimes. If we were looking at this in like X-rays, it would be a little bit easier to read. But looking at it this way, it's a little bit confusing because they've got all of the like templated calls and things like that that are a little bit, they're kind of painful to read. But anyway, so we have the, so we know that this thing was almost certainly PC. This might be the S, whatever that is, but I don't really care. I know that this was PC, so CPU read takes an argument of this, it takes an argument of PC, and then it looks like it probably takes, no, it looks like that's the only thing. So they read out a value. They check to see if it's 0. What does a set any do? Off the top, well, there's another way to find this out. Off the top of my head, I'm not exactly sure what set any does. What does set any do? So they do a read. If it is 0, then we're going to go one way. Otherwise, we're going to go the other way. So if it's 0, set it to 1. If it's 1, set it to 0. Okay. So if it is non-zero, we're coming over here. If it's 0, we're going over there. I can live with that. So if it is 0, we take CPU in here. We check to see if it's debug. If it is debug, we're going to print out no op, and then we're going to exit. So basically, this was the exit condition. They're going to go until a null byte, at which point it's a no op, and they dump out. Over on this side, we actually try and do something with it. So again, we check to see if we're debug. If we are debug, we're going to print some stuff out, it looks like. My guess is that this is probably going to try and like decode it, maybe? I don't know. But this is the debug output. And if we don't have debug output, we're basically going to step. So this is probably where the actual CPU does stuff. What is the actual CPU doing here? So we call CPU next. So RDI was, just to make sure, this was the this pointer, and there were no other arguments here. So this is CPU again. We put in here, we call it next. Then save off the return of next. If next is not this thing. So Josh has gotten back to me partially. What do I do with this? No results found. Does this do anything? No. Okay. Sorry, I'm poking around with the Binary Ninja stuff to see if I can get these things fixed up a little bit. Oop. So what exactly is this thing? Oh man, this is completely unreadable, isn't it? Yep, this is not going to work. Okay. So if I dump this in here, so I have no idea what this file is that oh, nope, this is not useful at all. Darn. So basically what happened there was Josh in the Binary Ninja Slack said set integer display type is probably what I'm looking for. Turns out it's probably not what I'm looking for, but I'm not sure what actually is. So, yeah. Going back to this, so we're comparing this to be some value. Unfortunately, I still don't know what this value actually is. It's a relatively large value. We tried to decode it, it looks like. If the return is above whatever this value is, we're going to say we don't know what it is. Otherwise, we're going to come in here, and this is the table for how to decode each of them. We're going to execute that. So basically what we're doing here is when we called this, it looks like it just takes some Z80 shellcode and it runs it, right? Where were we? So this is where we were, I think. Yeah, this is the execute command function. Execute command function in set objective. So what were we supplying is that? So we said RSI is this thing. RSI is this thing. We call Sterling on it. We will print out command received, and we will run it. We'll base64 decode it. So we actually, I assume, base64 encoded at some point here, right? Yeah, look at that. We base64 encode the code. The code is what we supplied in here. In this case, I said that that should be that. So basically what we're doing is we're just straight up running Z80 shellcode. The stage 1 here is going to, like I was saying before, it's going to load 1 into A. It's then going to write A to a memory address. It's then going to load a memory address into A. It's going to subtract 8, and then it's going to write A into a thing. I don't actually know what that does, this is Z80 thing. Let's take a look at that real quick. What does that do? So Z80. So I assume, like, I'm making some pretty general guesses here based off of what it looks like. If it's like other, yeah, looking at this, a load A BC is equivalent to move ALBX. It actually might not be, it might just be different mnemonics for the same thing, because they're basically the same architecture, I think. I don't know how old computers work. They're confusing and scary. So anyway, yeah, we put 1 into the A register. We then put the value of the A register into this memory address, which would be -6 or -10 decimal. We then read from negative whatever that is into A. We subtract. What does a sub with no arguments do according to Wikipedia? Oh no, they only have moves. I'm sure there's a yeah, let's see what this is. Because opening random PDFs I find on the internet are always a good idea. So this right here is a data sheet from Mouser, talking about a whole bunch of stuff. What I really care about in here is what a sub does. A sub A, oh, so it takes the A register, A is equal to A minus S. That's what I would have guessed. So they subtracted 8 from A. So they read that value in and they wrote it back. So what exactly did we just do here? So according to this, it enables debug and moves a vtable pointer to allow leak. And to leak vtable pointer easily. Use print memory instead of check secure code. Okay. Okay, so I assume what's happened. So I'm making some wild guesses here, based on this comment, that the offset at, so this is So, making some wild guesses here, the CPU structure has at some point a block of memory that we're going to access, and it doesn't bound check that a write is going negative. So when we write 1 to the negative 10 offset, we're going to actually enable debug. So what we should be able to see here then, if we come in here, we know what the debug offset is. Where is the debug offset? So if we come in here, the debug offset is... All right. Thanks. Okay, anyway. Oh, you know what I can do here? And I feel kind of... So I can do CPU run. Seriously? Oh, so I'm at the... So what? So we read out that value if plus E is 1. So this is the debug flag, is plus E. So based off of what the exploit looks like, so based off the fact that they're going to, the exploit claims that this will write to that. And if we come in here and I say, I want some Python here that I can run. So oxe that, except I want it in hex because reasons. That is 4. So basically, so FF6 is -10, like I was saying before. So oxe plus 10 is plus 24. So if we go step and instruction, RAX is now the CPU. Look at this. So at OE is the debug flag. That would be this. That'd be E and F. And then we go 10 more bytes after that. So 4 bytes, 8 bytes, 10 bytes. This is probably the start of memory then. If we look at what this was, we're looking for 3E01. 3E01. Apparently, I can't do math. But if we look at this, basically it did exactly that. So it wrote the command we sent it into memory. And if we dig through this, we can probably see that in this next, step, I guess? Yeah, it's probably in step. If we come in here, it's going to come over here. It tries to decode an instruction. And then there's a table here, which are all the instructions it knows how to decode. That's a lot of instructions. Come on. This is an int. It's an array of ints. Are you not going to let me just say you're an array of ints? So at this point, I've only got 15 minutes. I'm not going to actually look up what this does, but it's probably a safe assumption that whatever... And you got tired of me, didn't you? My VM has decided that going slow right now is the right way to go. So... Come on. Come on. I'm twiddling my thumbs like you can't actually see, but, you know, I'm sure you understand. Yeah, there we go. And it's back. So what they've done here is they've written whatever we give it into the memory. And if we dug through all of this, there's a lot of opcodes there to dig through. But what we would do here is we'd actually dig through them. If I was solving this without all the cheating, we dig through each of them to try and figure out exactly what is going on. And in this case, we already know, due to having the solution in front of us, that the LD memory instruction is going to let us read negative from memory. So in this case, we're going to read and write negative. So we wrote 1 into this. The FFE8. So what exactly is FFE8? FFE8 is negative 24. So coming here, minus 24, which is 6, right here. Yeah, so this right here is the vtable pointer, like I was saying. So it read in the value from the vtable pointer, subtracts 8 from it, and then writes it back into it. So basically, this is the vtable. So this is the vtable pointer for the CPU object, and it just shifted all of them over. And according to the comment, this is because that will print memory instead of calling check secure code. I'm not entirely sure what that does. I assume that this is to be able to leak things out easier. So this will leak the pointer to the linked lists on the heap. This way we can be able to leak the heap address, where we will put a new fake vtable. Looking at this code, it looks, so what are we doing here? We are compiling value. So this is basically building this up. This is, I'm guessing, also statically compiled. I was assuming that this would have to be done, like you were compiling this at the time, the first time I read through this real quick. It looks like that's not the case, that this is just a much more complicated piece of shellcode. So we're reading in a value, writing it out to a different location. Yeah, we're reading in from one location, we're writing it to a different location, and we're going to go through and do that over and over again. Okay, what else do we have in here? So we do that, we leak it out. They're going to use this to read memory. This is going to get a vtable pointer, calculate the base, it's going to calculate the got from that, calculate the printf address. It's then going to use dynelf, with a lambda, fancy, to actually leak out everything, then build a fake vtable that has binsh as well as the address. Trying to think of what this is. My guess is that this is probably system. I don't know off the top of my head, but that's probably a safe bet. So what it's going to end up doing is it's going to call system with binsh. Then we're going to set up another token. This time it's an empty. So what do we do? We load 1 into A, we load 0 into A, and nop. Okay. We read objective to initialize the objectives list. Then we're going to stage 2 to remove the objectives pointer into the vtable pointer. Okay. Oh, so we loaded the objective with the fake vtable. So we stored an objective, and then when we read it, we load it into the table. Then stage 2 is going to use that. We go in there again, and we pop a shell. Makes sense. Looking at the other exploit I see here, it looks like they probably do something relatively similar. What are they doing here? So, there's some case state there. So, this is what they sent instead for their stage 1. Oh man, they are like hand compiling this. Wow. Okay. Wow. So they looks like they're doing something very similar. So they move 1 into A. They then set this to be my guess is they're doing the same thing here. So they pack -10. Yes. So looking at what this looked like, Ocean's version moves that into -10 and loads it in. That looks like the same instruction there. Then a 3A. I don't know what 3A is. So a 3A where we're going to then go through and with a decrementing address. Okay, so basically they've hand compiled whatever the 3A instruction is with an address that is incrementally farther on, starting from -24. So that's where the V table would be. So they're blowing away the six bytes. I think it's bytes, probably bytes. They're doing something with the 6 bytes there. I don't know what, but they're doing something with it. So we are then going to receive until. So we set that objective, and then we're going to receive until that. Oh, that's clever. So they enable debug. So when it runs through that, it's going to print out what the vtable pointer is. Right. So if we think about what's happened here, we enable debug, and once debug is enabled, it's going to print stuff out to us each time. So the first time when we read in the first byte of that vtable pointer, it's going to print out what that value was, and here they're going to actually pull it in. So in this case, we go through, they turn it back into the integer value. This is the offset into the binary for what it is. So now they know that this pi is the base of the executable. Then they're going to set up a new object, this time with pi plus some magic value, and they're just going to encode the E3. Okay. Trying to think of what they're doing here. So, it's probably the same things, right? So in Ocean's exploit, they set up the. So once with stage 1 to leak stuff out, then the stage 2 is going to set up the fake vtable as the ID token destination. So this is the same thing, setting up a fake vtable. I don't know what this magic value is, but that's going to be the new vtable. Then set up a target objective, exactly the same thing. And this time we're going to set up some hand-compiled code again. And this time we're going to, what are we doing here? So starting from -8 in memory, we're going to do the same thing. We're going to read out more values. So for whatever reason, we wanted to read out some more values. The magic here is the address of our fake vtable, probably. And after we do that, we're going to compile some more stuff here. What are we doing here? So this is a 3E instruction with L is... I'm not sure what this shellcode is doing. So building some sort of a structure, and we're going to run some more shellcode. So basically, every time we call set object here, we're running some shellcode because we're supplying it with what to run. This last one, I'm not entirely sure what it is, but whatever it does, it's going to set it up so that when we run it this time, it's going to run binsh somehow. So that's that. It's a little unfortunate that I didn't actually get to solve this here. I basically just got to poke around, walk through some of the write-ups that were posted in IRC. Hopefully this was useful to people. What may be more useful is the actual start of this video. At the start of the video, for anybody who didn't join right at 7, what I did was I walked through real quick. I just pulled up some write-ups from last year's 0CTF. Because 0CTF is coming up this weekend. I think over here you can probably see me talking about that still. And basically just going through real quick, like, here's some of the crypto challenges that it looked at. The one that I thought was pretty cool was they had that RSA private key where half the key was hidden from you. And taking a brief look at some of the mobile challenges. So they had an entire category of mobile challenges. There were only 3 of them, but there was a category dedicated to mobile challenges, which were Android reversing challenges. The real reversing challenges, well, not real, or the desktop reversing challenges, they don't have many write-ups on the CTF write-ups, so I unfortunately don't remember them from last year. So I'm kind of going in blind for those. I vaguely remember a couple of them, and one of my teammates writing a whole bunch of IDaPython to solve it. The exploits, they had some heap challenges on there, as well as a sandbox escape. The heap challenge being a... Thanks, Jordan. That right there is the solution for getting the integers to work right in Binary Ninja here. So if I come in here, I can probably go doop. Oh, do I have to do this every time? Note that the one in the above assumes that the constant value is the second argument, which might not be true for some. Well, it worked once. It changed this one. But going back to what I was saying, like, the start of this stream is probably more useful to most people because I was talking through some of last year's OCTF challenge, zero CTF challenges, which is going to be useful because zero CTF is this weekend, this upcoming weekend, and I'm going to plan to spend most of my time playing it this weekend. I expect it to be a ton of fun. And going through some of last year's challenges helps put me in the mind of the developers to kind of know what they do when they write challenges. So again, thanks everybody for watching. Hopefully this was useful to people. If you have any comments, feel free to leave comments. You can send me a message on Twitter or on one of the many Slacks or IRCs. Basically on a lot of different systems. So if on the Binary Ninja Slack, some of the individual team Slacks, I usually use Murmis, IRC. There's a link in the video description. On Freenode, I go by Murmis. Feel free to send me a message. Let me know if you need anything or have comments or questions. So thanks everybody, and I will probably do this again next week with some wrap-up information from zero CTF and hopefully some challenges I can walk through that I've actually solved previously. So thanks everybody. Bye.